Hello and welcome to another episode of the Func Prog podcast with me, Christopher. And today I have with me a very special guest, Elisabeth Stenholm. Welcome to the podcast, Elisabeth.
Hi, thanks for having me.
Yeah, thank you so much for coming on the podcast. So first, for the listeners who aren't familiar with you and your work, could you please give them a quick introduction? Who are you, Elisabeth?
Right, so I'm from Sweden, from Stockholm, but currently I live in Bergen. I have a master's in mathematics from Stockholm University, and after that, the reason I came to Bergen is was to pursue a PhD in Homotopy type theory.
Okay, interesting. So, and like, we'll get into the nitty-gritty of all that later. But first, I just want to know, like, I mean, since this is a podcast about functional programming, how did you first get into functional programming?
Yeah, so I work with functional programming now. I finished my PhD and now I work as a software developer with functional programming, primarily Elm and F#. And how I got into functional programming was via the dependent type theory. So I was a mathematician who then got into dependent type theory to be able to formalize my mathematical theorems in the computer because I always liked programming. And then that way I got into functional programming first with Haskell, and now I do F# and Elm.
Okay. And like, so, okay, first you got into Haskell at university while you were studying.
Yes.
And and then you went on to like do, I was going to say harder drugs, but
yeah. Well, I did it kind of the opposite order. So I did the harder drugs first, which is Agda, which is like Haskell on steroids. That's how I usually explain it to people to do in a short way. And then I got into Haskell, which was, for me, that was like Agda, but without dependent types. So I kind of came the other way around from what people usually do.
Okay, so you kind of learned to like ride a bicycle and then you put the
training wheels
back on.
yeah, sort of.
But I guess a lot of like our listeners are familiar with Haskell, at least as a concept. But I mean, what is Agda?
Right. So Agda is, you can kind of think of it like Haskell, but with dependent types. So then, of course, you gotta know what are dependent types. A dependent type is a type that can depend on a value from another type. So the simplest case is the type of numbers from 0 up to n, like an actual number. So your input is a value, a number, positive number, and then the output is the type that contains only the numbers 0 up to that number. And this type you cannot construct on the type system level in a usual programming language. You can fake it sort of to have a private constructor and a validator that only constructs these values. But compile time, the compiler cannot represent a type that only contains these finite numbers. For any, where you can input a natural number and you get the type that only contains 0 up to that number. But with a dependently typed language, you can do this. So this means, for instance, like the prototypical example would be that you could have a safe get an element from an index in a list. And then you could take the index, instead of the index being an int, as you would usually do, you could say that the index should be a number from 0 up to the length of the list. And then this value, of course, varies depending on the list you actually have. So you cannot and you get this then on the type level, so on compile time. So that means that you don't need to do any runtime validations, that you don't do an index out of bounds, and you get the compile time security that this will never be out of bounds.
Yeah, that sounds really cool. I mean, because in regular and like even in a pretty powerful type, or if we like go take a step back, like in a lot of languages, you would sort of use like the runtime assertions for these kind of things, right? Like you would say that, or maybe throw exceptions if you try to do something illegal. Like if you try to access an element that's larger than the number of elements in a list, for example. But in like when you have a dependent type system, like the type system can check these things for you, right?
Yes. So you get this assertion compile time, and then so whenever you want to use this function that gets the index, you need to somehow convince the compiler that the number you're accessing with is actually within the bound compile time.
And is that a hard thing to do?
I mean, you need to get used to how to work with dependent types. So when you first try it the very first time, it's kind of a new thing, a new way or approach how to write code, because you're not used to writing dependent types. But once you get used to it, in this case with the index, in the list shouldn't be that hard. Depends on the index that you're actually trying to use here. If it's very difficult to show that it's within the bounds or not.
But like I guess the neat thing is that like if I understood it correctly, like if you have one part of the program where you can sort of show that like, okay, this index is I don't know, maybe it is a known number at compile time, or you can show that it's like guaranteed to be less than the number of elements in the list. That sort of information can sort of carry over to other parts of the program, right? If I understand it.
Yeah, so if you have shown, for instance, that I have a number here that I know is less than n, some number, then I can use this proof in other parts too that need this validation for the compiler to accept your code.
Yeah, or I guess like the thing that's a bit mind-bending for me, like full disclosure, I know a little bit about dependent types. I tried to read this book, The Little Typer, by Daniel P. Friedman and David Christensen, and I got a few chapters in, and then I don't know. I have to try to like do it again at some point, but it felt like my brain was starting to melt after a while.
Yeah, I think the best way to learn dependent types is just to choose some dependently typed language / proof assistant and just start working with it to get comfortable with it.
Okay, so you just like, go in and try it out.
Yeah, and it's gonna be, I mean, a bit confusing maybe in the beginning. There's a lot of stuff to learn, but if you have maybe a book or a tutorial or maybe someone that you know that can help you out a bit, then
give you a helping hand.
Yeah, it will start to make sense, hopefully, after a while.
Yeah,
it's just sort of a new way of thinking. It's kind of like if you go from imperative or object-oriented programming style to functional programming, you gotta sort of switch your mindset a bit, and that can be a big threshold from the beginning. And it's kind of like another step up from, so it's like functional programming on steroids. But once you get used to it, and you gotta work with it to get used to it, then it gets easier.
And I mean, you have been working with this for quite a long time. Like, do you feel that it has sort of shaped the way you think about programs? Like, do you miss dependent types, for example, when you switch back to Haskell?
Yeah, it has definitely switched how I think about programs. I think very much in terms of the types now. So when I try to, I don't know, construct a function or write some piece of code, I just think of the type, and I can get a lot of like information from just how the type looks. And also when I try to understand code, I usually look at the types. But do I miss dependent types in my daily life? I don't know. I feel like for like everyday programming, like what I do for my job, I worked for an insurance company. So there's a lot of APIs that we just send data back and forth. I feel like dependent types would probably be a bit overkill there. So I don't miss them there. But, and now I've also been working on a research paper for a revision recently. So I have been doing a bit of Agda. So I don't miss it yet. But I mean, maybe when it's been like half a year or a year since I did Agda, I might feel like, okay, I need to stretch my muscles here a bit.
Okay. But if we circle back to like your academic career, like you started with doing Agda, and then you sort of you did a bit of Haskell, but then you pursued a PhD in homotopy. Am I saying that right? Homotopy type theory.
Yeah, homotopy type theory.
Yeah.
Yes.
What is that?
Yeah, maybe some people have heard about this fancy term, homotopy type theory. So actually, I started with Agda after I came to Bergen. My first dependently typed programming language was what's now called Rocq, which was previously called Coq. I'm glad they changed the name.
Yeah, it was like, you know, a rare, like, I mean, because it was designed by Thierry Coquin, right?
Yeah.
And it was based on the calculus of construction. So I guess that, like, you know, that's where the name comes from. Yes. Yeah. But it has kind of like an unfortunate meaning in English.
Yes. So there's been a discussion, I think, for quite some time that they should change the name, and they finally did, which I think is good. And then Agda, if I recall correctly, was created after Rocq, and the name Agda comes from a Swedish song, The Hen Agda. And it's placed on that Rocq was something about a bird, and then they wanted something other about a bird for this new proof assistant. So
it's a rooster and a hen.
Yeah, exactly. So that's kind of fun.
But okay, so is this like homotopy type theory? Is that that has something to do with the proof assistant thing?
Yeah. So the way I can kind of give a bit of backstory to how I got into it, which maybe might help explain what it is. So I was doing mathematics, abstract mathematics, and then I wanted to, I learned that you could like have your computer check your mathematical proofs. And the way they did that was with dependent type theory. And there are different kind of flavors of dependent type theory. And one particular one is called homotopy type theory. How much like technical detail? I can go into a bit of what it is.
I want to go deep into the weeds. I want to know everything.
Okay.
The audience will just have to follow along, or they can shut off. But it's my podcast, so if you don't like it,
you can just turn
you can
off.
go listen to Joe Rogan or something.
Yeah, and also when it's a podcast, you could always do like double speed or like skip, you know, a couple minutes ahead. So if you don't enjoy this, then you can skip it.
Go listen to your normie podcast if this stuff scares you. Like, no, I want to get deep into the weeds. Okay, so there are different flavors of type theory.
So first of all, then I think we should sort of give a brief overview of how do you use dependent types to prove mathematical proofs. The thing is that when you have dependent types, you can encode any logical proposition that you might assert. And you encode it as a type. So a logical proposition for all x, blah, 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 becomes a type. It can be translated into a type. And in particular, you can you can construct a type that corresponds to the statement something equals something. And this is a dependent type because this type depends on the two values that you put on the left side and the right side. So you cannot do this in a normal language. But with a dependent language, where the type can depend on values, you can construct this type that says that this value equals this value. So this is not the same as your usual equals in your usual programming language, because that's just a bool, which is only a value. But here, this is actually a type. And
so it is an actual, like this equality is sort of a type in itself.
Yes, exactly. So you got the type of natural numbers and you got the type 2 equals 3. Those are like live in the same universe, sort of.
Okay. And I guess if just like, if we go back one step, like if you think about it and this isn't something that you usually think about like that much when you like just write ordinary programs, but like equality is first of all in most languages very limited, like, and it's and it's a bit weird as well, because usually equality is usually restricted to like a very like the domains of values. First of all, like even in functional programming languages, you usually cannot compare, even if you can compare two functions, compare two functions to each other, usually, like, the semantics of that is kind of weird. Like, I don't even know if you can do that. Can you do that in Haskell? Like compare two functions, say like, are these equal or not?
I don't think you can do that. And you got a general, like, theoretical issue with comparing functions. Some functions that are nice and that, like, where you can go through all of the cases that it will compute, you can check that they're equal, or if you, like, theoretically now, or if you can somehow prove that they produce the same value, you can show that they're equal. But, like, if you have a function that has an infinite input type, then it's not certain that you can compare it to another function.
Yeah, I mean, I just realized that functions cannot implement EQ, the EQ type class in Haskell, but because functions can't implement type classes, period. But
and you also have this issue that, you cannot necessarily show for all functions if they are equal or not. It's like an undecidable, but for some you can. Yeah.
Okay, so so now we have established that this is not your grandma's equality. This is something like
yes. So it's not the usual bool equality, but it's actually a type. And then the question maybe becomes, okay, but what then are elements of this type? Like if I have some element of the type x equals y, what does that mean? What's that element? And the way you should think about it is that that element is a proof that the equality holds. So the type x equals y contains any proofs that the equality holds. So you can construct, for instance, the type 2 equals 3, but it's going to be an empty type. It doesn't contain any elements because it's not equal. So there are no proofs that it's equal. And you can construct the type 3 equals 3, which then does contain elements because 3 does equal 3.
Okay, I see. And so the way you prove this is that you try to find find an instance of the type. Is that how you do it?
Yeah, exactly. So you translate your logical proposition, for instance, 3 equals 3, is my logical proposition, and then I translate it into a type, so this equality type, and then I prove it by constructing an element of that type, and then I've shown that the logical proposition holds.
Okay. And so is this one type of dependent type theory, or?
So this is just, now we're still at regular, so to say, what's called Martin Löf type theory. He's a Swedish guy who came up with this identity type, this equality type. And
is this also what's called like
intuitionistic type theory?
Thank you.
Yeah.
Type theory. Okay.
Yes, and we're not so far. We haven't sort of split into homotopy type theory. So this comes next then, because if we consider this identity type, let's say I have x equals y type, and then I constructed an element p, and I constructed another element q of this identity type, right? So two proofs that x equals y. These two are elements, and I can construct their identity type, p equals q. Like, there's nothing stopping me from constructing this type. I don't know if it contains anything or not, but I can construct the type. And then the question is basically, what is this type? What is equality between equalities? And then you have, and you can repeat this infinitely. So let's say you have alpha and beta of type p equals q, and then I can construct alpha equals beta type. And then I get this like infinite tower of equality.
Okay. Okay. So how do you get out of this mess?
Yes. So basically, how do we want to deal with it? How do we want to interpret this equality? What this should represent? And so, in my view, or one way of thinking about homotopy type theory is that this is one way of interpreting what this hierarchy means. So the way you do it for people who maybe have a bit of mathematical background, if you have some topology background, is that you think about x equals y, the type, as the type of paths, topological paths from x to y in a topological space. And then the type p equals q is then homotopies between these paths, and you get this whole hierarchy.
Okay. So you sort of try to model it as like a topological problem, like a graph, I guess, or
kind of like a mathematical space and paths between points in a space, and this then has some. Gets you to an axiom for how you want to sort of deal with equalities between types. So let's say I have a type A and a type B, then I can construct the type of equalities between these two types.
Okay. So the way is to sort of like, I guess maybe translate between the two, or?
Yeah, so that is the question. How do you interpret, what does it mean for two types to be equal? And this is not decided by the Martin Löf type theory itself. It doesn't. You can have several different interpretations that interpret it differently but still work. But with this sort of topological mindset, you end up with an axiom called the univalence axiom, which kind of says that to have two types be equal is that you can have a function going back and forth that ends up in the same spot, and you have an inverse that goes back and forth and ends up in the same. Like, you go there, you go back, you end up in the same. You start on the other side, go there and back, you end up on the same thing.
And I guess this is sort of like I mean, I'm not really good at these things, but it sort of reminds me of category theory and like morphisms, right?
Yeah, morphisms.
So, and what's the difference between like this, like the univalence, and something being a morphism, or is that like sort of the same thing, or?
So it's kind of slightly different things, but they also have a bit of overlap. So types together with functions form a category, a categorical structure, and then the functions are the morphisms in this structure.
Ah, okay. Mm.
So you can sort of view this from a category perspective with category glasses if you want to.
Mm.
But it's also kind of slightly separate things.
Yeah, I see. So, I mean, what are the sort of the advantages of homotopy type theory, or what does it let you like do that you can't do in the into no, there's that word again. In Martin Löf type theory.
Yeah. So you can prove some things. Like you need this univalence axiom to prove something. So for instance, we were talking about equalities of functions before, and it's not in plain Martin Löf type theory. Equality between functions is not like I have a function f, I have a function g, I construct the type f equals g. What are elements in this type? And that is not defined. Like there's no answer to this in plain Martin Löf type theory. You can have different models that give you different answers to this, but both work. But when you add the univalence axiom from this topological interpretation, you can prove, after adding that as an assumption, this assumption that equality between types is that you can have these maps back and forth. When you add this to your type theories as an assumption, then you can prove that equality between functions is that they are equal if they map everything to the same thing. So you only need to check every point of the function. And then if you can prove that for any input, they give the same output, then you show that the functions are equal.
Okay, so I guess a really simple way of this is sort of, I'm thinking of something, I think it was Philip Wadler that used this as an example, like in the, what's that paper called? The theorems for free.
Yes, theorems for free, yeah.
Like if you have for example, if you have a function that's like the identity function that takes like, you know, a value of a type x and gives a value of type x back, like no matter how you would like formulate that function in code, like it's all of those functions are essentially the same function, right?
Yeah, that's true. That is not, you don't need, it doesn't have to do really with the homotopy type theory or the univalence axiom. He did this not in HOT, so far as I recall. I read this one recently. So it's just holds without the univalence axiom.
Yeah, but I guess that's like, you know, a very simple, like the sort of the simplest version of this is that like if you think about it, like if you sort of any function that gives the same output is sort of the same, like given the same input is sort of the same function, right? I mean the like the, I don't know, the definition itself is not that doesn't really matter if you think about it.
Yeah, so this theorems for free paper basically it says something about polymorphic functions, so functions that you define for an arbitrary type where you don't need to know anything about the type. You don't use any information about the type. You just make it for an arbitrary type. Then he shows that there are some things you can know about these functions that they have to satisfy.
Okay, so yeah, but you don't really need the univalence for
No.
this. It's just comes out naturally. I see. But how does this relate to like something else that you often hear is like something called the calculus of constructions? Is that also this? Like, how does that relate to the different type theories? Or is that the same as the Martin Löf?
I don't remember all the details of the calculus of constructions. It's not the same as plain Martin Löf type theory. There are some added things, and this is, by the way, for the listeners, this is the type theory that Rocq is based on. So it has some specific constructions that you can do. So it's not the same. This is like, again, another sort of flavor. I don't remember the differences exactly between what this has as opposed to plain Martin Löf type theory as it was originally defined.
Yeah, I guess I think this is one like a maybe the simplest version or something. Yeah, I'm not sure, but one thing that I think is kind of like fascinating in independent type theories, like, you know, in order to be able to sort of prove all of these things, and an essential part is that you sort of need to be able to sort of run the program at compile time, if that makes sense. Like you need to be able to like simplify functions in order to show that they are equivalent, or that you sort of get the same thing on both. Like if you want to say that this expression is like equal to that expression, you sort of need to be able to reduce both of the expressions to see if they are equal, right?
Yes, yeah. So you need to. I mean, it's for me that has a background in mathematics. It's basically that I'm writing a mathematical proof. How would I prove on paper that these two functions are the same? I need to somehow reduce them, maybe do some cases and show that they always end up mapping to the same element. And I just do this sort of in code with the pentatypes. And then so the compiler then, if I use Agda, for instance, as a proof assistant, then I only type check my program. So the compiler just checks that all the types line up. Every element, if I have an element and I say that this element has this type, then it checks that it actually has this type. So if everything type checks, then that means that your proof is correct, because the values, so the types are propositions and values are proofs of these propositions. Yeah. So you just need to type check that the values actually have these types, and that means that you proved your proposition. So that's
another Wadler paper, right? Like propositions as types.
Yeah, so this is I thought this was so fascinating when I got into type theory at the end of my master's. It's something called the Curry-Howard correspondence, also, or types as propositions as types is another name for it, which is this like one-to-one correspondence between mathematical propositions and what they correspond to as types. It's basically this translation that I was talking about translating your propositions into types.
And so how does that work? Like, or what's the basic idea behind the Curry-Howard correspondence?
Yeah. So let's say, for instance, the idea here is to think of elements of types as proofs, basically. So concretely, let's say I want to prove I have my proposition P and Q. the proposition that both P and Q are true. Then let's think about what is a proof for this proposition. Well, a proof of this would be two things. It would be a proof that P holds and a proof that Q holds, right? So elements, or the proofs here, are pairs of proofs for each of them. And this then is the same as if you go to the type side and you think of this P and Q as a type, the type that it corresponds to is the product or tuple. So it would be the tuple of the type for P and the type for Q, because elements of the tuple of P and Q are tuples. It's an element of P and an element of Q. So a proof of P and a proof of Q. And similarly, if I have, for instance, A implies B, that then is the type of, the corresponding translation is the type of functions from A to B. How does this make sense? Well, what is an implication? It's basically some sort of black box that lets you input a proof that A holds and it will output a proof that B holds. That is a proof that A implies B. So on the type side, this is a function then. So a function from A to B, where A is the type of proofs of A, and then it outputs proofs of B.
So basically, if you can write this program and execute it to completion, that sort of means that you have proven that's a proof of the proposition, basically.
Yes, so you don't actually need to execute it, you just need to type check it. So if
yeah, that's true.
Yeah, so if I, for example, I wanted to show an implication, I don't know, that 3 equals 3 implies that 3 equals 3. This was kind of stupid, but let's say I wanted to prove that. Then what I would need to do in Agda or some other proof assistant was to take then the type 3 equals 3 and then function to the type 3 equals 3. So I need to construct a function from 3 equals 3 to 3 equals 3. And that is easy to do. I can just send whatever input I get to itself. And then I type check this and it goes through. And that means I proved that 3 equals 3 implies 3 equals 3.
Yeah, I mean, it's how can I say it? I guess it sounds simple on in theory, but I mean, it's I mean, for example, if you have, I've been thinking about this. There was this tweet that I've been thinking about for like way too long. There was this guy who. It's been literally living rent-free in my head ever since I saw it. There was this debate, classic debate of, strong type systems versus rigorous unit testing. And there was this tweet that said something to the effect of like, I mean, types are great, but like you cannot type check that FizzBuzz like something outputs gives you the correct output. But then I was thinking about it, like, I mean, like, no, I think you can actually. And I mean, this is the I guess this is like you could produce like, given that you have a FizzBuzz program, I guess you could write like a proof that if I input any number that is like divisible by 3, I will always get fizz back, unless it's like divisible by 15 in case, and then I will get FizzBuzz. Yeah,
you would be able to actually prove that with a proof assistant or dependently typed language. Then you could prove that this holds, and then you don't need all of the unit tests, which will not be able to cover everything because it's an infinite input possibility here. So, but you could prove it with dependent types. But the thing you cannot get with dependent types, and that you can never get, is sort of the semantic stuff that is in your head. So, for instance, if I wanted to write a function print foo or whatever, and it should always print foo, then I can, of course, show that it always prints foo, but the information that printing foo is the correct thing to do, in this case, that is semantic information that I need to, that is in my head. So like that the function behaves as I imagine it to behave, that information needs to come from the programmer. If you understand what I mean.
Yeah. I mean, I guess it's the same thing with, like, you know, that famous Charles Babbage quote when someone asked him, like, you know, if I put in the wrong numbers in your calculating machine, will the right answer still come out?
Yes. Yeah. That was actually a good analogy.
No, I think programmers have been struggling with this from the beginning. Like, you have to start with a correct spec first of all.
Yes, because that one the computer can never do for you. Like, take your idea from your head. That one you need to somehow express. But then you can check that the way you like implemented it gives you the output you expect.
Yeah, but something else I was thinking about is, like, you know, when you have these dependent type systems, there are a bunch of things that you can't just do, right? I mean, things like unbounded recursion or exceptions or I/O. You can't just have that, right? Independent typed.
Right. So, yeah, you cannot have I/O in a purely, or any side effects if you are like purely functional. So in order to be able to have I/O, you need to go outside the purely functional. But you, of course, if you want to do some executable code, you will need to have side effects. But at some point, yeah. But if you only do proof assistants, so you only prove theorems, then you don't actually need to execute your code. You just need to type check it.
Yeah, tell me a bit more about that, because that's something that I haven't really wrapped my head around. Like, you know, so if you run, like, if you're writing an Agda program, you don't actually run it. Is that correct, or?
Yeah, you don't make an executable and run it. It doesn't do anything on your computer. It doesn't print anything. It doesn't, you know, do any side effects. So you just basically do the first part of the compilation, which is just checking that everything type checks. So a regular compilation would first check that everything type checks, and then it will go on to build the thing. But here you sort of just do the first step.
Just you know, check that everything. But I guess the thing you have to remember or like keep in mind is that, like, you know, since it is dependent types, like, they are much more expressive than regular types. Like you said, like, you know, the things you can express in the type system is I mean, quite a bit more than you can in, like, I don't know, like Haskell or. But I guess, although I guess, like, Haskell has a lot of, like, this language extensions that you can sort of use to get it closer to dependent types, but
yeah.
But I also understand that, like, when these proof assistants, that they can give you a bunch of help when you're writing the program as well, or like how does that work?
Yes. So all the proof assistants I've worked with so far have some sort of possibility for interactive programming. So it looks slightly different in the different ones. I've been using Agda most during my PhD, so it's what I'm most used to. And Agda is kind of like Haskell, but dependent types. So what you do, you can actually do this in Haskell too, sort of. In Haskell, you can do an underscore. I don't know if you've ever tried this, but I want to, I set up the skeleton for what I want to do, and then I put an underscore, and then it will tell me, I will get a compilation error, but it will tell me what do I need to fill in there and what do I have in scope at that point. And it's kind of like that in Agda. I can leave, in Agda, I leave question marks, and then the type checker will type check everything as much as it can. And it will not give you a complete thumbs up because you still got these things you need to fill out. But it will tell you, okay, here you have these and these things in the context or in the scope, and you need to give me something of this type. And then I can sort of work my way inwards. So, okay, I need to, construct P and Q, like we talked about before, like a tuple P and Q. And then I sort of, okay, that means that then I need to construct a P, and I need to construct a Q, and then sort of work my way to smaller and smaller pieces until I can fill everything out.
Okay, so you can sort of build the program interactively.
Yeah, exactly. So I type the skeleton, and I put question marks where I don't know yet, and then I have a keyboard shortcut in Emacs, which type checks the whole thing, and then it gives me interactive locations in the editor. And then I can go into them, see what I need to fill in there, and then I fill in something with some more question marks inside there, and then I type check the whole thing, and then it gives me a thumbs up, okay. Or maybe not a thumbs up, and then I slowly work away these question marks until hopefully everything is without question marks.
Yeah, I mean, that sounds like a really cool way to develop programs, I think.
Yeah, but you can do this in Haskell as well with the underscores. I actually do that. That's probably influenced from me coming from Agda to Haskell. But I love doing that. I write the skeleton, and then I'm, instead of doing... I remember when I learned Python, that was the first language I learned. It was pass, I think, right, in the function. So I set up my functions, and then I just write pass in the body. So it's kind of like that, but I just place underscores, and then I'm like, okay, I'll fill that in later.
Yeah, let me deal with that.
Yeah.
At some other point. I mean, yeah, there's this book that I've been reading, working my way through slowly, called like Type-Driven Development by Edwin Brady. And it's about Idris, which is like a kind of like something in between like a regular programming language and a theorem prover. And you also had a great presentation about that at Func Prog Sweden that I will link to. The users can check out. But have you worked a lot with Idris?
No, not that much. I did do the thing that I presented on the presentation that you will link to. And before that, I hadn't done much Idris, but it was kind of familiar because it's a dependently typed language. And I do think that Idris today is probably the choice if you want to do executables. So like there are two ways you can use the dependently typed programming languages. You could use them as theorem provers, or you could use them to write executables. And for executables, I think Idris is probably the one to go for.
Yeah, because he talks a lot about this like way of working where you sort of like you define the type first, and then you leave a bunch of holes, and then Idris kind of like goes in and like helps you fill in the holes, and then you get more like like you said, then you can sort of like you keep drilling down until you sort of have a finished program.
Yeah, so you can work in Idris like I do with Agda, fill out bit by bit because it's not like you have it's not like you write code, from top to bottom, like a book or whatever. You need to sort of, okay, I need this function that should kind of do this, and then drill down.
Yeah, but I guess that makes sense because, like, I think in general, when you write functional programs, it is more like a tree, like that you're sort of working in a tree of code. Like when you write like a procedural program, it's more like top to bottom, like do this, do this, do this. In like functional programs, it feels more like you are sort of navigating this, building up this tree structure that works with other tree structures, etc. So I guess
you're kind of doing small like blocks or boxes, and then you like put them together in the end to form a big box that does what you want from beginning to end.
Yeah, then you have the whole forest.
Yes.
But have you tried Lean, like the new version of Lean 4?
Yeah, I've tried Lean. I am unsure which version I tried recently. I think it was Lean 4.
Yeah, because as far as I know almost nothing. I'm just following like Twitter hype. I see a lot of people talking about Lean 4, but should probably be that one, because as far as I understand, there was quite a gap between the prior version and this one, and they changed it quite a bit. Because that also seems to me like a language that can be used both to write like regular programs, but also as a theory improver, which sounds like quite interesting.
Yeah, so I mean, even Agda can also be used to create executables, and I think you can do executables with Rocq, but Rocq and Agda are mostly used in practice as theorem provers, even though they have support for making executables and I/O and that kind of stuff. But yeah, Lean, I think, as you say, try to do both theorem prover and executables. I haven't written any executables with Lean. I've tried it as a theorem prover, and I used it to give an introduction to theorem proving for the mathematics master students at the University of Bergen.
Oh, okay.
So these are like old school mathematics students. They work on pen and paper, and I wanted to give an introduction to how they can verify their proofs in the computer. And then I chose Lean for that, because it's a very ongoing, very active community, and it has a large library of already formalized mathematics, like basic building blocks. So you don't have to start from scratch.
Yeah, they have that mathlib thing, right?
Yes. And it's quite large, and I actually like, they use a lot of nice functionality like type classes, like Haskell, that just makes it nice to, like, it makes it a nice user interaction to work with this language. Because even if you have, a dependency type language, there's also the part about actually working with this, the tooling and everything. And Lean is very good there. Like the tooling is very nice. It's very user friendly, but it's like if you do theorem prover, if you use it as a theorem prover, there are two sort of different styles of how you write the code.
Okay, yeah.
So in Agda, it's kind of like writing Haskell code. I want to construct my element of my type that represents my proposition. And I just construct the element like I do in Haskell. If I need to construct a function, I construct the function like in Haskell.
Yeah, just write the function.
Yeah, just write the function. And while in Lean and Rocq, you usually do what's called tactics-based theorem proven.
Okay.
And that is more kind of like it's more along the lines of how you write a mathematical proof on paper. It's like first this and then this. It's like you're going from up to down and like writing not a story but a proof line to line. First this and then this and therefore this and therefore this. So it's a different style, but I think Lean also supports doing it the Agda style / Haskell style, just writing the function. But you can also do it like in the more story style.
Okay. So is that because I've been wondering? Is that what tactics are like? The like sort of that the proof assistant sort of helps you with the, or like allows you to write the proof in a way that's not really like a program, or how does that work?
Yeah, so kind of both those things. So a tactic will try to construct. So in the end, even in Lean or in Rocq, you still need to construct this element of the type you need. But instead of like manually explicitly constructing that element, you're sort of using the tactics, which are like helper functions or functionality that will try to construct this element for you. It just needs you to provide it with the input that it needs. So, and you do it in you kind of, it's the same thing there. You kind of go into smaller and smaller parts, and then in the end you get to fill out like a trivial part, hopefully at the end, then everything works.
And do you have like specific like because it like I said, I'm not very familiar with Lean, but it looks like you can use like different kinds of tactics. Like, I don't know, I saw someone mention a tactic called like grind or something. I was like, wow, that looks intense.
Yeah, so there's of course predefined tactics from the standard library or the standard Lean installation, but then you can also define your own tactics. So there's a tactics definition language. So you can, for instance, you could do your own specialized tactics for your code. You can combine tactics into bigger tactics. So there are these fun tactics, and also I remember them from when I did my master's in Rocq. Also there you can define your own tactics, and there are these like massive combined tactics that are basically like try everything tactic. Just tries anything.
That's brute force.
Yeah, and they can sometimes be surprisingly effective, which is kind of, that's kind of fun actually. To I need to prove my theorem here, and then I just write try everything tactic, and it just works.
Yeah, it feels like cheating almost. Or
yeah, but it only works in the cases where this proof is kind of straightforward. Maybe it's a lot of steps, but it's straightforward. There's no like trickery involved in how you need to prove it, and then it can do these things. But if there's trickery involved or some sort of creative way of proving it, then it's not going to be able to solve it.
So the tactics can sort of get you the last mile, so to speak, like to help you finish up something, or like just save you from doing something trivial yourself. Is that?
Yes, and they also can help you along the way. So I need to prove this, and then it can help you get started. And then I use a tactic, and it says, okay, I can prove this, but then you need to provide me with this smaller thing instead.
Okay. You sort of like, okay, given that you supply this, then I can help you finish the thing.
Yeah.
Okay. But Agda is less like tactics focused. That's more like...
Yeah. So in Agda, you need to explicitly, manually construct this actual element. While with tactics, the element is being constructed in the background. So you don't see what it actually is. The tactic is constructed for you.
Yeah. And I mean, if someone, like we touched on at the beginning, like maybe the best way to learn this is like, just to start. But which one would you recommend starting with of the ones we've been talking about so far?
Right. So I would say that depends on, first of all, what's your background, and second of all, what do you want to use it for? So there's you want to use it as a theorem prover, or you want to use it as executable, which is like functional programming on steroids. So for executables, well, first of all, why would you want to use dependent types for executables? What do you get, sort of, that you don't get? What you get is that you can completely, perfectly model your domain to make illegal states unrepresentable. You cannot always do that in usual functional languages. You can usually get quite close, but sometimes it's impossible to completely represent it, like the index of the list, for instance. You need to just use an int in regular languages, which is, of course, then there are some illegal states there, which are the ints that are out of range. But so with dependent types, you can get this very strong compile time assurance because you can model your domain completely. But dependent types are slightly more complex. I mean, with great power comes great responsibility and all that. So you have a lot of expressivity, but also some extra complexity. So, but if you want to try to make an executable with dependent types, then I would say Idris is probably the way to go. Maybe Lean. I shouldn't say that Lean is not good because I haven't tried it for executables. So it might be that Lean is actually also nice. I've only tried with Idris so far. But Idris, I know I have the impression that they sort of focus on it. They try to make it an executable language.
Yeah, I mean, because I guess that was a stated goal from the beginning, I think, like to be able to sort of bridge these two worlds.
I think so. Yeah, that's my impression too. And it's not it's not a large language, so in that sense the tooling might be better for Lean 4 at this point than Idris. So Lean 4 might be a good choice. Again, I haven't tried it, so
it seems like they have invested a lot of like money into building this, and like like David Christensen that I mentioned before, he has written a really good tutorial, I think, that's called like functional programming in Lean, that I've sort of also made like maybe read 3 chapters of, which is sort of my I don't know, story of my life. Read 3 first chapters of everything.
Yeah, I do that too. Yeah. But I recommend also just jumping into it and trying to code a bit.
So something that I wanted to, like, that I've been thinking about is, and this is gonna be like really specific, but like something that took me a bit of time to get used to is this idea of type application, or what I mean is like, I mean, if you're used to, like, I don't know, language with generics or something like that, like, I mean, usually the parameterized or the type parameter is something that sort of lives like beside the types, like, but as far as I understand, in dependently typed languages, the type itself to like a generic function is usually one of the function parameters. Did I get that right?
Yeah, yes, you are onto something here. So in independently typed languages, because as you say, like, the natural numbers is a type, but then, like, what type does type have? Sort of.
Yeah.
Which independently typed languages gives you an infinite hierarchy. So natural numbers and integers and strings and list of integers, they all live in the type called type, or whatever it's called in the proof assistant you're using. And then that is itself a type that lives inside another type that is like type 1 or next level type. And then that lives inside type 2, and then you get an infinite hierarchy. And you sort of have explicit access to this hierarchy. You can work with this hierarchy in your code, which you usually can't in regular languages. You just have access to the first basic level types, but you can't work with the higher universes. And you usually don't need to, on like an everyday regular basis, work with this whole hierarchy. Yeah.
Yeah, but that's sort of like one of those ideas that sort of like feels really like far out. Like there's a it's sort of like, okay, so everything is a type except a type, which is like a universe element or something like that. I mean, it sort of stacks infinitely, right? Because all of the what do you call it? Like values are have a type, and types have are like instances of the universe of types, and that but those elements are also elements in there. And I guess
types, exactly. All elements have a type, and all types lie in a universe, and that universe lies in another universe. So a universe is just another fancy word for a type that contains other types.
And is this a way to sort of get around Russell's paradox?
Yes, I was just about to get there. Yeah, so this goes back to Russell. So it's very similar to the paradox. I don't know if you've heard about it, or the readers or the listeners have heard about it, that you cannot say that the collection of all sets is itself a set, because that gives you a paradox. And it's very similar to that. So you cannot say that, all the types, they lie in some type. And you cannot say that this type lies in itself. Because that will give you essentially Russell's paradox, the one for sets. So then you need to say that this type lies in some other type. And that type needs to lie in some other type. And then you go on and on.
Yeah, because otherwise you could do something like, I guess the problem is sort of like self-reference, that otherwise you could say that like, oh, this is the set of all sets that contain themselves, sort of.
Yes, that do not contain themselves.
Yeah, that do not contain themselves.
Yeah, and then you ask, does this set that I just defined contain itself?
Yeah.
And then you get a paradox. Yeah.
Yeah, and like you said, for like, the everyman dependent type theorist, like, or if you want to write like practical programs, maybe this doesn't show up as a concern that much, like, unless you want to or is that correct? Is this more like when you want to do like advanced proofs that you sort of can leverage this like homotopy type theory? Or
this comes up more in advanced mathematical proofs. If you do executables with dependent types, you're usually, so there are some types where this equality hierarchy by itself stops at a certain level. So for instance, the natural numbers is a type where any two equality proofs that you can construct are equal. But you don't need to assume this for all types, but it holds for the natural numbers specifically. Those are just like a nice type to work with.
Well-behaved.
Yeah, it's a well-behaved type. So usually when you do executables, you're only working with these well-behaved types. So then you naturally don't need to worry about this whole hierarchy.
Yeah, I mean, speaking of executables, I kind of want to circle back to something we talked about before, which is like what do you think about the utility of dependent types for like everyday programming? You said something like, you know, it could be like a bit overkill, but do you think they will, like, you know, do you think they will ever become mainstream? Like, as in, like, do you think this would be a tool that becomes popular outside of like academia, or do you think it's going to be more like a research thing?
Yeah. So I mean, it's always hard to say, but I don't see it becoming as mainstream as like Haskell or the big programming languages, simply because it's extremely powerful, and you can go wild on the domain-driven design.
Yeah.
But it is more complex, and it's harder to learn and harder to get used to, and also sometimes it can be harder to understand the compilation errors because it's the type checking is more complex. So sometimes the compiler is not able to give you good compilation errors. So, and for most regular purposes, I think it's good enough with as long as you have algebraic data types. So, as you do in functional programming, so you need your some types / discriminated unions, as they're called in F#. When you have those, you can do a lot. So you cannot do everything, but yeah, I think it might be slightly too complex to become mainstream. But what I do hope and think is that in academia, I hope and think that it's going to be more and more mainstream for mathematicians to verify their proofs in proof assistants.
Yeah, like we talked about Terry Tao before we started recording, and he made waves because he was doing a lot of like, I think he was formalizing some of his theories in like Lean or something like that. I mean, he was pretty like, I don't know, he was posting a bit on like, you know, that he was using Lean for in his mathematics work. So is that something that kind of thing you were thinking about, like?
Yeah, that's exactly what I'm thinking about. Like so far in the proof assistants, in my experience, have been most commonly used by people who are sort of already into type theory. So like me, I have a master's in mathematics, but I started with type theory in my master's thesis. So I was, you know, into type theory, and then I was using proof assistants, while the regular pen paper mathematicians that weren't into programming weren't necessarily using theorem provers. But I hope that will become more and more mainstream, because it does give more confidence in the mathematical proofs. And if you've ever tried to formalize a mathematical proof, you quickly realize that it's very easy to write on paper something like, yeah, the rest of this is left as an exercise to the reader, or this is trivial to prove. And then you actually go and you need to prove it, and the computer is not forgiving. It needs all the details, and then you realize, okay, well, maybe this wasn't that trivial after all. You thought you had it, you know, but then you get there and then you're like, oh, right, I didn't think about this case. This is not trivial. That has happened to me. And I also have a story of when I was trying to prove something with my supervisor during my PhD. And then it didn't work. We weren't able to convince the computer, the theorem prover, the Agda, that this holds. But we had already had the paper where we claimed this thing accepted.
Oh, okay.
It hadn't been published yet, but it had been accepted. And we were like, yeah, we should probably formalize this. We didn't manage to formalize it. And then after keeping on trying, I was like, maybe this isn't true. And then it took me a couple hours, and then I was like, okay, I have a counterexample. Damn.
Oh no. So what happened to the paper? Did you have to retract it, or?
Yeah, we retracted it. And we still haven't solved that specific thing that we were trying to do, but we have, something else sort of came out of it that we are hoping to get published soon. So there was a paper that came out of it, which is kind of, yeah, but we had to do some modifications.
Okay, yeah. So you could still salvage the some parts of it, but like, yeah. That's very, very interesting. Like,
so that is the lesson to all the mathematicians out there, that you really want to formalize your stuff to be like completely sure. Because I mean, if we were to sort of, as a community, go together and formalize all the mathematical theorems that we have proven so far in humanity's lifetime, then I'm sure we would come across things that don't work in some theorems, some details that we haven't thought about. I don't think that we're gonna, everything is gonna fall apart and we're gonna realize that nothing works. I think we will be able to salvage things, but I'm quite sure, after having formalized my own stuff, that there are mistakes there. They are probably fixable, but you get so much more assurance in your mathematical proof when you formalize it.
So yeah, that's the message. Like, if you work in mathematics, you should download Lean 4 and.
Yes. So this kind of circles back to a question you asked, where I kind of answered one half and not the other. Where should people start? So if they want to get into dependently typed languages, and if you want to use them for theorem proving, then I would say, if you have a background in mathematics, so you're like pen and paper mathematician, then I would probably go with Lean, as you said. I think that's a good one. It has a good large library, it has good, nice tooling, and the way of writing your proofs in tactics is closer to how you're used to writing them on pen and paper. And that's also how I started, because I started with Rocq, and that is also tactics based. And then, but if you can also prove not just mathematical theorems, but you can prove things about your program. So if you're a programmer and you want to prove properties about your program, and you're used to writing functional style, maybe Haskell, then I would probably go with Agda.
Yeah, because the onboarding from like Haskell to Agda is, because Agda is quite similar to Haskell, right? Like in the way you write it. And
yeah, the syntax is quite similar. And then you would be probably confused about the tactics way of writing it if you come from a functional programming background.
I see. So yeah, that makes sense.
Yeah.
Yeah, I mean, I think it was like an interesting point there, like, what you said about, speaking of like Haskell, etc., and whether the dependent types would go mainstream or not. Like, do you think there's something that dependently, like regular languages, could like sort of steal from dependent types, so try to integrate into like more mainstream languages, if we're not switching to dependent types wholesale?
Right. So maybe something. So what comes to mind is that Haskell kind of has stolen some dependent types with their. They have so many language extensions, but if you use some of them, then you can get some dependent types-ish, which can be useful. Again, in specific cases when you want to express something that is actually dependently typed then you can get more close to it. So that's nice. Otherwise, maybe I have felt, I don't remember what I was writing, but I remember one time when I was writing Haskell, and I just wanted to be able to use this whole hierarchy of the universes,
Okay, yeah.
and talking about types, like using types as my values. But again, I don't remember what exactly it was. It wasn't anything crazy, but it would have been easier or nicer if I could just manipulate that. But so that could maybe be something. You don't need to have a full dependently typed system, I think, to... Well, do you need that? Okay, unsure. Maybe you won't be able to have the hierarchy without dependent types, but perhaps.
Yeah. I don't know. Have you looked? I mean, you've been doing a bit of TypeScript as well, right? Or did you get to touch that yet?
No, I haven't touched TypeScript, and I'm not a front end gal. I'm more back end. So the front end stuff that I do is basically for my job, which is Elm.
Oh yeah, that's right. You're using Elm. That's
yeah.
I forgot about that.
It's a super cozy language. I mean, it's kind of a love-hate language. Some people love it. Some people really don't like it. It's Haskell style. It's very functional and tries to be as, properly functional and as you can and as pure as you can until in the end when you need the input and output.
And so how do you feel about Elm?
I like it. I don't have much experience in front end, so I cannot say that I can sit here and compare it to other front end frameworks. And I am very biased towards functional programming, but I like it. It's as someone who likes Haskell, I think if you like Haskell, the chances are you're gonna like Elm for front end.
And it's a bit interesting because as far as I understand, like Elm sort of dials down the power of the type system a bit compared to Haskell. Like it doesn't have type classes, for example.
Yes, it is sort of weaker in the power of the type system. That is true, and that actually I have missed sometimes. I have, been thinking Haskell in my mind and trying to do something the Haskell way, and then I can't in Elm. But it's usually expressive enough to be able to do what you need to do in front end.
Yeah. I guess maybe you can sort of like compartmentalize the code a little bit more to sort of like so it doesn't have as much of an impact as if you didn't have it on the back end.
Yeah, and if you need to do some really advanced stuff in the back end, then you could have a separate back end for front end or something, and then have Elm just as a front layer, and then leave the complexity to the back end.
Yeah, that's true. I mean, I think this is kind of an interesting question. Like, it feels like, it does feel like, at least for any given problem, there's sort of a sweet spot on the power spectrum of like the programming language or like the type system. I mean, so like if you go too far on one end, it's like not powerful enough. But if you go too far out, like you risk it becoming like too powerful, and I mean, you can express more things, but you sort of get other trade-offs, like maybe the compile times, or like you said, the type errors become harder to understand, etc.
Yes, exactly. Yeah. So there's definitely a trade-off, and I don't think there's a one size fits all here. I think it really depends on what you want to do, the context. So the question about will this be used in mainstream? One usage I can see of dependently typed languages in to do executables in industry. That would be basically very security sensitive software that you need to be very sure that it is correct. And then there are different ways of formally verifying software. But one way that I am kind of intrigued by, but I haven't tried much yet, is that you write your code together with a proof that it behaves as expected in a dependently typed language, and then you can use a software that extracts the actual program executable part of that. So there's this project, Agda to Haskell, currently active. It's on GitHub, where you do this. So you write your code in Agda, maybe, I don't know, a sorting function for lists, and then you prove properties about it. And then you can use the Agda to Haskell program, which then extracts Haskell code from this, which extracts the actual executable part of this, but forgets about the proof.
Okay, yeah, so you just get like sort of the thing that's actually runnable.
Yes, but then because it was extracted from this code where you had the proof too, you can be sure that this code, assuming that this extractor part is correct, you can that this code will behave as expected.
Yeah. I mean, that's would be nice.
Yes, but that's of course more expensive and time consuming than just writing the code without doing these proofs. So, in your regular old job, you probably don't need this, and it's going to cost more than it's worth it, probably. But, maybe in, I don't know, flight software or something, where it's very, you need, there are big consequences when it goes wrong.
Yeah. Or maybe didn't they make like a formally verified C compiler a while ago?
I don't know.
I think there was something like that. It's like a C compiler where like it's like proven to actually be correct. Because I think that could be another one where you sort of like the number of different inputs you can get to the program is so vast that it's like kind of hard to predict like how the actual program will behave, and like bugs in a compiler is usually not very nice. Usually you want to be able to eliminate the compiler itself as a source of errors.
Yeah, for sure. I haven't heard about that, but that sounds super cool. And it makes sense that because then you can focus on making the compiler secure, and that is like a foundational building block that then other stuff.
Yeah, and that's a really good point actually, because usually when you write the compiler, you do a bunch of things to sort of make it. You always need to maintain correctness, and the ideally the program output should be, or the semantics should always be preserved. Like you just maybe want the program to run faster, or want the compiler to run faster, and then I guess maybe the having writing it in a dependently typed language, or having like a parallel proven implementation, I guess could sort of work as a play the role of like a test suite almost, sort of like make sure that minimizes regressions.
Yes, and it covers the proving something formally covers more than you could cover even with for those who are into testing, even property-based tests won't be able to cover all cases when you have an infinite possibility for inputs, but you can cover everything with a formally verified proof.
Yeah. Yes, I guess that's like the strength of the actually proving things instead of just, because otherwise it's like a bit haphazard, just you know that it works for this input, but maybe not the one after that, so to speak.
So it's like in my head, I have this, it's this hierarchy of how sure am I about this piece of software. So first you have like not writing any tests and just relying that I did this right. Okay.
Yeah.
Vibe
checking.
Vibe coding. Yeah. And then next level, you just write some test cases, manually. And then, of course, that's better than nothing. But it just covers those cases, and maybe there are some cases that you forgot. And the next level would be something like property-based tests. Have you ever used those? You generate the test data.
Yeah, I haven't. I've played around with it a bit, like with Python, for example. But I know there are really mature implementations for like Haskell and F#.
Yeah, so we actually are kind of testing it out in my job currently with F#. So the idea is that you generate the test. You write a function, the logic of how the test data goes together, but you do it with random generators, but you can specify very much how these values are generated. So you can, specify I want an int between 3 and 6 or something. And then the property-based test, when you run it, it will generate, in fscheck, for example, the basic setting is 100 tests, where it generates a bunch of different like legal inputs and tests it. So you get, of course, much more test coverage than writing the manual tests. But you're still not as secure as when formally verifying. Then you're like 100%. Well, asterisk, 100% sure. Because, of course, your theorem prover could have a bug.
Yeah.
But assuming that it doesn't, then you are like 100% sure, and you know that you're covered all cases. Otherwise, there might still be some cases that you just missed and were unfortunate, and the tests went through anyway.
Yeah, I heard that Lean 4 is implemented in C++, for example. So there's a...
Yes, and story time again here from me. I found a bug it was in Rocq.
Okay.
Actually, that was kind of, but I, props to them, or fairness to them, I was using an experimental feature, but that they had labeled in the documentation as this is still, experimental.
Work in progress. Okay.
Yes.
So what happened?
It was a bug. To me, I just got a message like, this is a bug that should never happen. Please report this at this GitHub. And then I reported it, tried to make a minimal example. And then some of the developers were like, I managed to, construct an element of the empty type, which if you manage to do that, you can prove anything.
Okay. Yeah.
That's not good. But they fixed it.
Okay, so the patch then. Yeah, they should implement it implement Rocq in Rocq.
Yes. I mean, this is kind of interesting. Or, they could implement Rocq in Agda and Agda in Rocq. And
Yeah. I mean, I think that's could be the topic of a whole different podcast episode, like the like this, because eventually you run into like Gödel's incompleteness theorem, right?
Yes. So you won't be able to always, like, you're gonna come to some sort of bedrock where you just need to trust it, / in mathematics or in philosophy where you just assume some axioms or something. Yeah. So it's an impossible task to try to get to something where you're like 100% sure with no trust issues.
Yeah, because I mean, I guess the essence of that is that you cannot define a system in terms of itself, right?
Yeah, so you cannot prove the correctness of a system from within itself. Yeah.
So you have to rely on axioms.
Yeah, or you have to, if you want to prove the correctness of a system, you have to prove it from within another system,
Okay, yeah.
basically.
So you have to rely on axioms or hacks.
Yeah, and so if I want to prove my system correct, and then I need to work within another system or a bigger system to prove that this is correct. But then, of course, I need to trust that the bigger system is correct to be able to trust this proof that the inner system is correct.
Yeah, I would like to come back to that, tell that to my Scrum Master when he asks why the feature hasn't been delivered yet.
Using this.
It's first I have to I want to be sure.
Yes, I think that's definitely gonna go down well.
Yeah. I think all the other stakeholders, they will also understand. Yes, of course. It's
But I was wondering, didn't they? I feel like one of these dependently typed languages is actually bootstrapped on itself. Let me give you just 1 second to just, I think maybe lean. Okay, 1 second.
I think Edwin Brady implemented Idris 2 in Idris 1, I think, or something like that.
Yeah, it might be Idris, yeah.
I should really get someone like Joe Rogan has, Jamie. Jamie, pull that up. Check. Is that true, Jamie? Is Idris implemented in Idris, Jamie?
That would be practical.
Yeah, I mean it's. I guess it's it's like the bootstrapping compilers, should work. Yeah, I guess we're running out of time, but one thing that I would really like to see, just as an example, is that that thing in Lean 4 where you can evaluate an expression and get the result back right in your editor. That would be super useful. I wish language would more languages should steal that.
Yes, and maybe also this interactive way of programming, where you do it incrementally and just fill out holes. I mean, Haskell has this with the underscores, but it's not. I mean, generally, the programming community are not used to programming in this way. So that we could take from the theorem proving community of working interactively with the editor to write our code.
Yeah, and I would like to see this both at the type level and the value level as well, because I think that would be super useful. Because I mean, what we do, Elisabeth, every day, a lot of that is we transform data, for example. You get the JSON blob in, and you're supposed to produce another JSON blob out, and a lot of the time it's the only way to figure out how this works is to sort of either write at unit tests or break out the repo, which is really unnecessary indirection if you think about it. If you had this a total, I guess the issue is that you kind of need you sort of need to have some kind of rein in the side effects a little bit for this to be useful, because you don't want to accidentally make calls to the production database while you're sort of playing around with code in your editor. But given that you have that, I mean, I don't know. That's one thing I would really like to see, at least.
Yeah, for sure. I mean, I haven't thought about that, but that would actually be quite convenient to have. I agree.
Yeah, totality, massively underrated, I think. more programming languages should be total. Yes, and have to mention as well that you are coming here to Stockholm on October 15th for the big Func Prog conference.
Yes, I'm very excited. It's so nice that you guys are creating a functional programming conference.
Oh, thank you.
For all us nerds out there. So I'm looking forward to it a lot.
It's like, I would really like to see a functional programming conference in Stockholm, and I mean the way for like general functional programming. I mean there are a bunch of other ones here as well, like for example the esteemed Beam conference, the old Erlang user conference that has its own home in Stockholm, but like for people who are more into Scala, Haskell, etc. There hasn't really been anything, so I'm super excited about this as well. And a big thanks to like Magnus, who from Homotopy, who's helping us with the thing, and I think it's going to be awesome.
Yeah, thank you for making it happen, and I also think it's going to be awesome, and I look forward to also hearing the other presenters.
Yeah. No, I think it's like we have just gonna go ahead and sell this here. Like we have a great lineup. We have you. We have Giacomo, who's gonna come on and talk about Gleam. We have Daniel as well, who's gonna known from Rocq to JVM. He's coming. He's gonna talk about effect systems in Scala. I think it's gonna be amazing. Tickets can be found at funcprogconf.com, and I hope by the time you're hearing this that there are still left, because they are running out. I guess that's enough.
That's
enough
a good
sales pitch.
Yeah, no, but that's nice, and also just come and hang out. I'm looking forward to also just meeting other nerds.
yeah, like who are these people? Like the all
functional weirdos. Yeah,
all the 12 functional programmers in Stockholm gathered in one place. Can you believe that?
Yeah.
But
be fun.
Yeah, it's gonna be great. But until then, where can people find you, Elisabeth?
Well, I'm not super active on any particular location on the internet. I do have a web page, but that is very much under construction and not as much content there. I mean, you could check out my presentation that I had for the functional programming meetup if you want to learn more about Idris. You can... my PhD thesis is not going to be maybe for many people because it's kind of niche and advanced.
But who knows? You can check that out as well. It was about what was it, encoding sets in a homotopy type theory, or
yes, and especially non-well-founded sets. So that's like sets that can contain other sets ad infinitum downwards.
Oh, okay.
Yeah.
That sounds interesting. We'll make sure to link to it in the show notes. But yeah, I guess that's it. I will see you on October 15th.
Yes.
And I hope to see a bunch of listeners there as well.
Yes, I do too.
Yeah. Until next time.
Yes. See you later.